Hi everyone. In this video, I'll be covering the material for tutorial 9, specifically on the duality and KKT conditions, which we didn't manage to fully cover during our tutorial session. So in this video, we are going to talk about the SVM formulation, specifically on how to formulate the SVM problem and why we need the dual representation for SVM, as well as we will show to you on specific conditions for this dual representation to be helpful for us, as well as on some more properties on the dual problems. Okay, so in the lecture, we have seen the derivation of the SVM, and we want to also see how we can actually go about the technicalities of converting this into a dual problem and why the dual problem is needed specifically. Okay, so let me refresh your mind a bit with what we discussed in the Lagrange multiplier tutorial, which we have seen about some primer on optimization problems. Now we are going to see how we can denote an optimization problem in the standard form. When we say standard form, it means of two certain factors. First of all, this must be a minimization problem. Second of all, any constraints that is provided must have 0 on the right hand side. And specific for the inequality constraints, this must be less than equal to. Okay? So what this means is that if you see f0, the function that you want to minimize, this is what we call as the objective function. And then everything under the subject to, this is what we call as the constraints. There are two types of constraints. The first type of constraints is what we call, this is the inequality constraints. So any inequality constraints must have 0 on the right hand side, as well as it must be a less than equal to 0 for it to be in the standard form. And then we have, this is what we call the equality constraints. Okay, so for now, what I want you to think of is whenever you see me writing f, okay, whenever I see an f, f0 represents the objective function, fo, then any f value, this is representing the inequality constraints, any g value here represents the equality constraints. Okay, then now I want to explain a bit on the notation side, which I will use today. This optimization problem is what we call the primal problem. So when we say primal problem, a primal problem is essentially what is the original problem without any tampering with. Okay, so we haven't modified the original optimization problem, just probably that we only modify the standard form only. Okay, so this is what we denote by the primal problem or the original problem. With respect to the primal problem, we have this following notation that I want to introduce. First is basically your x star. Okay, note that this x star itself is essentially another possible value of x. But the moment when we denote a star, this represents that this x star itself is an optimal point. Whereas if I denote a p star, note that p itself is not a factor, so it's just a certain value. This is what we call the optimal value, or also denoted as the primal optimal value. Okay, notice that p itself represents that this is the optimal value for the primal problem. Okay, so it's also important to note that this is the optimal value that is subject to the constraints. Okay, so normally when we say optimal point, if we do not have an optimization problem, it can be, say for example, the global optimum. But the moment that we have certain constraints, this becomes our optimal value. So if we want to denote this in a mathematical manner, you will notice that this p star itself, p star is essentially the result of finding the infimum value across every possible x of the objective value subject to the inequality constraints and the equality constraints. Okay, so this is essentially telling me for any possible value of x that satisfies the constraints, I want to determine what is the lower bound for the objective value, the highest possible lower bound of this objective value. Okay, note that we are using here the infimum operator instead of the minimum operator. Why is that so? There is very slight differences among the infimum operator as well as the minimum operator. Let me denote it by this certain example. Let's say for the minimum operator, if I want to find what is the minimum value of any possible x within this interval, 0 to 1 inclusive, then the minimum value of x, this will just be 0. Okay, because now this has a lower bound, right? Then if I take the infimum of x, this will also be 0. So in this case, both of them are interchangeable. But the moment that say I have, this is our interval, let's say this is now an open interval from 0 to 1. So it's not inclusive of 0 and 1. Or if you want to see it in another notation, this will be any value of x between 0 and 1. The moment I want to find what is the minimum value of x, now you notice that this no longer exists. Because I can always find any value of x that will approach 0 but not touching 0. So if I put, say for example, if this exists, then I can just divide this by 2 again, then I will get a smaller value. I cannot say that min x is 0 now because 0 is not part of our set. So this minimum of x just simply doesn't exist. Okay? Note this. So the minimum value of x here just simply doesn't exist because it's not part of the set. But if I find what is the infimum value of x, now this is equal to 0. Why is this so? Because this infimum operator is simply what is the greatest possible lower bound for my set. So if I try to find what is the lower bound, then I will reach the point of 0. This will be my lower bound such that every single x inside here will be greater than infimum of x. Okay, greater than equal to infimum of x. That is how we define the infimum operator. Okay, I hope this clarifies the difference of infimum and minimum. Now for this tutorial, I will also introduce a slight notation change. So notice that here, your equality constraints is, we denote n as the number of equality constraints, whereas m as the number of inequality constraints. So I will change this thing a bit. That is, I want to denote the number of equality constraints that I have. This will be denoted by p, solely because I will use n quite a lot in this tutorial. So I just want to make sure that it's a bit notation difference here. So the number of equality constraints is given by p, such that if I want to find the infimum here, then now this I would be for all I in 1 to m, as well this will be for all I from 1 to p. Okay, so this is essentially just listing down all your m inequality constraints and all your p equality constraints. Okay, so now let's move on to the first problem today. We are going to write down the SVM primal problem for the standard form. That is, you want to find what is the objective value, what is the objective function, sorry, and also all the inequality and the equality constraints that are associated to this primal problem. Okay, so it's important to also note that in this problem, we assume that the data itself is linearly separable. There are two conditions here the moment that this assumption is failed. First one is you might have a data that is not linearly separable, but it's still separable in some way. That's when we have the kernel trick. Then another case is when it's not separable at all. Then that is where you will see a soft margin SVM is needed, which is in your section 2 of the tutorial. Okay. So we assume that this data is linearly separable. We want to see how we can formulate the SVM problem. So I will introduce an approach that is slightly different from the lecture by Prof. Harold, in terms of saying I want to actually show you how to derive the primal problem from the start, which is from the ground up. Okay, so let's see how the SVM works. Essentially, if I have, say, this is our data. So your data itself will consist of some positive training samples as well as some negative samples. We denote, say for instance, this is the two-dimensional data. So this is the first feature, this is our second feature. Plus represents a positive sample, as well as negative represents, this is our negative samples. Here, say for instance, if I want to draw a decision boundary. We have seen in the lecture that if I have two decision boundaries, let's say this is my first decision boundary, compared to say this is my second decision boundary, then logically we would say that the second one seems better than the first one. But we want to quantify why is the second one better. Okay, imagine like say for instance these are like trees. These are trees that are inside the park. Then I want to draw a highway across the park. Okay, if I draw it in a purple line, then I will notice that this will be quite a narrow road because I can only extend my highway to this point. else it will already contradict with my examples. Compared to if I draw it on the orange line, then I will have some more leeway. Okay, so this is where we introduce the concept of SVM. We know that the orange line here, the second line, is a better decision boundary, solely because if I can draw like some kind of a highway, some kind of a leeway from this decision boundary, this is like the widest point possible. Okay, so that means if I draw another line that is parallel to this decision boundary, such that this line will touch the first positive case, as well as this line will touch the first negative case, we want to maximize this margin. Okay, I repeat, this is where we want to maximize this margin. That's why terminology-wise, one important thing to note is that SVM is what we call a maximum margin classifier. That means we want to determine what is the decision boundary such that it will maximize the margin between the first positive case you see and the first negative case you see. Okay, so once we have defined that SVM itself is a maximum margin classifier, I will still use this following example. Let's denote the orange line as our decision boundary here. Now we know that SVM itself is we want to maximize this margin. But how do we formulate this as a mathematical problem? So here is where we will start to go back in the paradigm of factors. Let us denote two factors. The first factor is essentially a factor that is perpendicular to our decision boundary. So I can have this factor here, which is perpendicular to the decision boundary. Let's call this factor as W, okay? So W is essentially a factor that is perpendicular to the decision boundary. Whereas I will have another factor, we call this factor as factor U. So this U itself, you can imagine U as any point within our Cartesian plane or within any part of this plane. Let's call this as U. Okay, this is U. So U is essentially any point on this plane, then we are going to take the position factor of that point. That means it's a factor that starts from the origin and ends at that point. Okay, so let's denote U as this is simply any unknown factor. For now, you can think of it like this is the position factor of any point U. Okay, so once we have denoted these two items, my goal now is to first show you how we can denote the decision boundary in terms of these two factors. Okay, so let me give you some cases. Can I denote the decision boundary as just in terms of U? So can I say that if the length or if the magnitude of factor U exceeds a certain constant, then it is positive. If it's not, then it's negative. Can we denote it like this? So I can have, for example, if this U itself is long enough, then it will be a positive case. Whereas if this U is quite short, then it will be a negative case. At some point, you think that it is possible. But if I can have, say, for instance, this is a long factor, right? Then obviously this will be a positive case. But I can also have a factor that extends to the other side. Then if it falls below the decision boundary, this should be negative. Okay, so what I'm trying to show here is simply I cannot use just the length of the factor to determine whether it should be a positive or a negative case. Because note that this length would denote some kind of a circular constraint. Okay, that is essentially what I'm trying to show. So how do we better denote whether this should be a positive case or a negative case? What we can see is what if we can take the projection of this factor with respect to the factor W that is perpendicular to the decision boundary. Okay, so if I say, for example, this is our factor W, which is also the same factor you have seen just now. Okay, let's denote this is our factor W, then this is my factor U. Okay, if I can at some point find what is the distance of U or the length of U when I project it to W, or rather what is the length of U in the direction of W, then this will be a better metric. Okay, because now I can have a large enough U. Say for instance this is a very long U, but if I project it onto W, then it's just simply this length. And you see that this now falls below the decision boundary. If I have u as another long enough this part, if I project it to w, then it will look something like this length here, which now, since it exceeds a certain constant, it exceeds the length of this decision boundary, so it will be positive. Now this will be a better metric to think about. Okay, so we are going to go with this metric. That means my decision boundary can be such that if I find the length of projection of u onto w, if this exceeds a certain constant, then this will be our decision boundary. Okay, so if the length of the projection of u onto w exceeds a certain constant, then this will be a positive case, else this will be a negative case. So this is just a very rough idea on the orange decision boundary. Okay, so how do we find the length of a projection? That is where we will introduce our good old dot product. Okay, how is a dot product defined? Say for instance I have two factors. Let's call this factor A, and then this is factor B. Okay, this factor A as well as factor B. Let's call this angle theta. Dot product is defined such that if I have A dot B, so A dot B, this is essentially saying if I can know what is the dimension of these two factors, so they only work on factors of the same dimension, I want to do an element-wise multiplication of every element in A with every element in B. Okay, so AI, BI. That means this is A1 times B1, A2 times B2, so on and so forth. Then I just sum them up. Okay, or you can also see this in matrix multiplication as this is just A transpose, so this will be a row factor or a row matrix multiplied by a column matrix B. Okay, so in this tutorial, actually, you will also see me using this notation instead. So another way of thinking this dot product in a geometric manner is using a formula that we have learned in high school or maybe in MA 2001. That is, if I have the dot product of A and B, this is essentially saying the magnitude of A multiplied by the magnitude of B multiplied by cosine theta. Okay, so this is the length of A times length of B times cosine theta. What does this represent? Note that I'm only going to show you this part, which is the A cosine theta. Remember that if you have a normal, let's say, right triangle, if this is theta, say for example, this is the hypotenuse, this is the adjacent, this is the opposite, then cosine theta is given as what is the adjacent over the hypotenuse. That is, if I do H cosine theta, then this is just the adjacent. So when I do A cosine theta, then that is simply saying this is this part. If I draw a certain right triangle directly onto B, then this part is just your A cosine theta. B itself is given as this length. So this is your B. Okay, so the dot product of A and B is simply the length of this A cosine theta times the length of B. So now if I want to project U onto W, that means I want to find what is just this length, right? Which is just basically U cosine theta. That is why we have to find, if I want to find the U cosine theta, this is just the dot product of U and W. I divide this by the length of W. Okay, so this is essentially the key idea that I want you to get. That means if I say I take this W dot product U, then I divide this by the magnitude of this W. If it exceeds a certain constant, then we know that U is a positive case. Okay, that is how we define the decision boundary. But note that if I vary the U and I keep the decision boundary the same, then I will always divide by the same value, which is your magnitude of W. So technically I can treat this magnitude of W as a constant, and for now I will disregard this. So I'm just saying that I can just multiply this W to the right hand side, then I will notice that this will still be a certain constant. Okay, so now this becomes my decision boundary. Finally, I want to shift another thing here. That is, I can shift this constant to the left hand side. Now the right hand side will be 0, and that would be much better to handle. Okay, so when I do that, I can shift the constant to the left hand side. Now this will just be U dot product with W plus a certain constant, if this is greater than 0, then U is a positive case. Okay, so I will just put this in a certain box. I'm just saying that this will be what we call our decision boundary. Okay, I hope this is quite clear enough. So this will now be our decision boundary. Just to repeat, our decision boundary is just if I take the position factor of any point, I find the dot product of U and W plus a certain constant that I want to optimize here. If it's greater than or equal to 0, then U is a positive case, else it will be negative case. Okay, so now let's try to see how we can train to find what is the W as well as what is the B. So for this, I will utilize the training data that we have. That is, we already have some points that are positive, some points that are negative. But note that any positive point, I want it to exceed a certain point. So any positive point must not fall inside here. But I want it to fall exactly at where the purple line is. Okay, so now I will denote this item. We denote that this decision boundary for any positive case plus B, okay, I want this to hit the purple line. I don't want it to hit the decision boundary, okay? So I don't want it to hit the orange line, but I want to hit the purple line. That's why this will no longer be greater than or equal to 0, but let us set this as greater than or equal to a certain value. Set this to be 1 first. Then I will also have, if I have a negative case plus B, this must be less than or equal to -1, okay? So this +1 and -1 is just for me to specify that this will hit the upper purple line as well as the lower purple line. Okay, so once I have these two, if you notice, handling two inequalities is quite a troublesome method. So what I'm trying to do is, can I combine these two things together into just one single inequality? This is where I will be using an extra variable. So I'll be using what we call the target. Okay, we set target of a certain, say for example, target of a certain data point. This will be defined as a piecewise value. This will be equal to 1 if xn itself is a positive case. This will be -1 if xn itself is a negative case. Essentially, this is just your sine function, with xn being positive and xn being negative. Okay, so by setting this, I can multiply this across to the to each part here. So if I multiply this by Tn, let me just shift things down a bit. Okay, so I can multiply the above two inequalities with Tn. Now this will become, this is just Tn times W dot x plus B greater than or equal to 1. Since this is x plus, then this will just be multiplying by 1. Okay, so essentially this is just this is the same. Now what if it's a negative case? The moment it's a negative case, then I'll multiply this by Tn also. So now this will be -1 times W dot x minus plus B is less than or equal to 1. -1, okay? So the moment that this happens, then I can just simply, oh sorry, the Tn must be multiplied to both B also, okay? So put the wrong bracket here. So the moment this happens, then I can just divide both sides by -1 or multiply both sides by -1. Then this will be Wx times dot x minus plus B. Now the inequality flips. This will be -1 times -1, that is +1. Okay, notice that now these two things are the same. Okay, so once these two things are the same, then I can just establish that I can set Tn with the dot product of any data point x plus B must be greater than or equal to 1. Okay, or I can shift this one around to the left. So this is just saying this is Tn W dot x plus B must be -1 is greater than or equal to 0. Okay, so I can just basically shift this around. What I'm saying here is basically any positive case must be above this line. Any negative case must be below this line. Now what if I want to determine just that line? Okay, I don't want to determine what is above that line or below that line, but I want to hit just this line. So the moment that this hits this line only, then we know that there must be one positive case and one negative case that hits the line. Why is that so? Because if there's no positive case that hits the line, I can always shift the line top until I hit a positive case, right? Okay, so what I'm saying here is just basically there must be one positive case that hits the line. Okay, so the moment that it hits the line, that is when this inequality is essentially just an equality, because that is when it hits the line. Okay, inequality is basically I'm saying that it's above the line or below the line, but the moment it hits the line, okay, or I will say that if xn hits the line or hits the bounds here, then I can say that Tn wxn plus b minus 1 must be equal to 0. Okay, so this is for me to determine how to set the bounds, or how to set the, you know, the limits or the walls of your highway. Okay, so this is how I can set the bounds. Just circle this out first because this will be an important case. Okay, so now once we have established what is the gutter or the highway here, the next thing I want to do now is to determine what is the margin. Okay, here I will just draw the exact same thing, but now I will be using two important factors here. So it's just the same thing. I will draw this as my decision boundary. Then these are the two margins that we have seen, or the two bounds, the two walls. Now there will be a positive case here, then there's a negative case. Okay. Now I will add two other factors that we have. Let me just draw back the W case here. So this is our W, which is perpendicular to the decision boundary. I will utilize two additional factors. The first factor is essentially the position factor of the positive case. This is our x plus. The second factor is the position factor of our negative case. We call this x minus. Then I will have another factor here. Let me use another color. Let me use pink. Yeah. So the factor that connects the negative case to a positive case, this one now we can denote this in terms of x plus and x minus. That is, this just whatever the position factor of the positive case minus the position factor of the negative case. Okay, so we note that this x plus minus x minus, okay, this factor, the pink one, is essentially connecting from this bound to the upper bound. Okay, so try to let that sink in. This factor, the pink factor, will always connect from the lower bound all the way to the upper bound. If I can find the distance of the factor that is perpendicular to the decision boundary that connects the lower bound to the upper bound, then I'm done with my width. Okay, my goal is to find what is this width. Can we do that? Obviously we can, because just now we have introduced that we are able to find what is the projection of one factor to another factor. Notice that this W is just the factor that is perpendicular to the decision boundary. So if I can find the length of the pink factor that is in the direction of this W, then that is our width. Okay, so I'm just write that thing in. I want to find the length or the magnitude of our the magnitude of x plus minus negative x in the direction of W. This is our width of the highway, or the width of the gutter. Okay, so this is our goal. How do we do this? We utilize the same dot product identity here. So our width is essentially the dot product of this factor, our x plus minus x minus. Okay, we do a dot product with the W. All in all, we are going to divide by the magnitude of W. So I just put the division here. So for those of you who have realized, W divided by magnitude of W, this is essentially the unit factor of W. Okay, so this will be of length 1. So we want to find what is x plus minus x minus dot product with W divided by magnitude of W. Okay, so I'll utilize some property of a dot product here. That is, I can actually just split the dot product across x plus and x minus. So if I do this, then it will just be x plus dot W minus x minus dot W divided by the magnitude of W. Okay, this is the same thing. All I need to do now is to find what is this x plus dot w and what is the x minus dot w. Okay, so let's try to see that. I will utilize the orange equation here. So I'll use this. So we notice that if x is a positive case, then Tn would be equal to 1. That means I will have this is w dot x plus b is equal to 0. Minus 1 equals to 0. If I shift the constant to the right hand side, then I will notice that this is just w dot x plus is equal to 1 minus b. Now for a negative case, if it's a negative case, then I'll put this is my w dot x minus plus b minus 1 is equal to 0. So I can just multiply the negative inside, then I will have this is w dot x minus the negative of this dot product is essentially 1 plus b. Okay, so this is basically positive w dot x plus, this is negative w dot x minus. So I'll just put this back into the original item here. So the width is given by, this is x dot w positive, so this is 1 minus b. Now this is negative x dot w, so now this is just plus 1 plus b over the width, which is, this is over the magnitude of w. So if I get this all done, then I will notice that this is just 2 over magnitude of w. Okay, so what is this 2 over magnitude of w? This is just the width of the lower bound and the upper bound. The two purple lines, this is the width. So if I want to define the margin as what the lecture defines, then the margin is just half of this. So it's just 1 over the magnitude of w. Okay, so now we have defined the margin. Once we do this, the next thing to do is to just optimize this margin. Now, since we know that SVM is a maximal margin classifier, we want to maximize this margin, which is 2 over w, subject to certain constraints. So what are the constraints here? The constraints is simply, notice that for every single data point, it must be correctly classified. Okay, so that is just the simple constraint that we have. That is, remember, this is our decision boundary. Decision boundary is saying that if I dot product any point with w plus b must be greater than or equal to 0. Okay, or rather we can have this point also. This is just another point that says for any value of x, if I multiply wx plus b with the target minus 1 must be greater than or equal to 0. Okay, so I'll just apply this. The constraint is simply, I will put Tn, let me just use blue here, Tn w dot xn plus b minus 1 is greater than or equal to 0. Okay, so this is the problem that we have. All I need to do is to just make this optimization problem in its standard form. Okay, so first I will try to modify the objective function. We notice that maximizing 2 over w, this is just simply, I can remove the constant. Now this becomes maximize 1 over w, magnitude of w. Okay, so I'll just maximize this thing, which essentially is just, since it's a fraction, if I want to maximize this whole thing, my numerator is the same, right? The only thing I can vary is my denominator. If I want to maximize this fraction, then I want to make my denominator as small as possible. So then this is just our minimization problem. So I want to minimize the magnitude of w. Okay, my final change is that this minimization problem, I will make this as, I will put a constant here. Then I will put w squared. Okay, the only reason I can do this is because this w is essentially, this magnitude of w is taking for every single element here. I will do w1 squared, w2 squared, so on and so forth. Okay, note that if I want to handle a square root, it might be a bit difficult, so then I will have to square this out. Then this half is there for mathematical convenience, because when I want to differentiate this, then the 2 will cancel out. Okay, so the only reason that this squared can be done for our minimization problem is because if you notice, the square root function will look like this, right? Okay, square root will look like this, which is always monotonically increasing. Okay, which is always monotonically increasing. Same goes with your x squared. It's going to be if you want to minimize this, then it's just simply minimizing your x also. Okay, so that is essentially the reason why we can just square it out. Okay, so now once we have this whole thing, then I can just rewrite this entire problem. So I will just write this as our SVM problem in standard form. Primal in standard form. The problem is just we want to minimize 1/2 w squared, the magnitude of w squared, subject to, for every single data point xn, if I do a dot product with w plus a certain constant, multiply this by the tn, minus 1 is greater than or equal to 0. But notice that this is not in standard form because of this is a greater than or equal to inequality. So I just need to multiply this by -1 on both sides. Then I will have the final one, which is just 1 minus tn w dot xn plus b must be less than or equal to 0. So this will be done for every single n from 1 to whatever the size of our data set is. And now we have derived the SVM primal problem. Okay, so let me just put a note here. Basically, this is to ensure that inequality is, or maybe I just put ensuring that fix is less than or equal to 0. Okay. Okay, so now this is our SVM primal problem. Next thing is that we want to find out what is the Lagrangian for this problem. So remember that in our Lagrange multiplier tutorial, what we have shown is that if I have any problem, okay, if I have this optimization problem, I can actually multiply what we call the Lagrange multipliers to each of the constraints to obtain what is the Lagrangian. Okay, so actually, if you notice, the Lagrangian itself, Lagrangian is just your weighted sum of the constraints. That is, instead of having to consider each constraint individually, what I can do now is just I incorporate all the constraints together into one single function. Okay, so this is just the weighted sum. What do we mean by weighted sum? Weighted sum is simply, I want to sum them up, but I want to sum them by a certain weight. So this weight is given by the Lagrange multiplier itself. Okay, so when we do an optimization problem with inequalities, the same thing actually applies. We're going to multiply each inequality by a certain Lagrange multiplier, as well as each equality constraint by another Lagrange multiplier. Okay, so we denote lambda and nu here, such that the lambda I is essentially the Lagrange multiplier for constraint, for ith inequality constraint, whereas your nu I is essentially just the Lagrange multiplier for the ith equality constraint. Okay, so these are just we try to separate the two notation together because I want to separate out the multipliers for inequality constraints as well as the multipliers for the equality constraints. The reason why we separate is actually going to be given in the second part later on. So we also denote a factor here. We call this as our boldface lambda. This is just the factor of all lambda i's, and this is the boldface nu, which is just a factor of all the nu i's. So if you don't understand this notation, this is just basically a factor notation that tells you that, say for example, this nu factor is just a factor that contains nu1, nu2, all the way up to nu p. Okay, so this is the factor lambda and factor nu. This is our Lagrangian. Then one thing that you might need to note down is that this lambda and nu now becomes what we call this will be the new dual variables. Now, we want to consider what we call the Lagrange dual function. So earlier what you see, this is what we call the Lagrangian or the Lagrangian function. But now we want to consider what is the Lagrangian dual function. So when we say the Lagrange dual function, it is basically just a function that depends on your dual variables. So the dual variables is defined here as just basically your lambda as well as your nu. So what is this Lagrangian dual function? We define the Lagrangian dual with the lambda and nu. This is essentially what is the lowest possible or the lower bound for every single x of your Lagrangian. Okay, so essentially I'm taking this Lagrangian. I want to check every single possible x that is present. I want to find what is the lower bound of our Lagrangian, given certain lambda and certain nu. Okay, so that is our Lagrangian dual function, which is essentially converting the Lagrangian function. We eliminate x by finding what is the lower bound for this Lagrangian function. Okay, so here we are going to write down what is the Lagrangian as well as the Lagrange dual function for this SVM primal problem. How do we do this? Essentially, this is just template matching. So the Lagrangian would work given the optimization problem in the standard form. Earlier, we have already defined your primal problem to be, this is the, let me just write down. The primal just now is essentially you want to minimize your 1/2 magnitude of w squared subject to the constraint that is 1 minus Tn w dot xn plus b is less than equal to 1 for all n from 1 to how many constraints we have. Okay, so this is just the primal problem. Now from this, first of all, we want to derive what is the Lagrangian. If I put in the template, your Lagrangian of x, lambda, and nu, this is just basically your objective function plus multiply each inequality constraints by lambda plus we multiply each equality constraints by nu. So this is for all I to p. Okay, so this is to the number of inequality constraints that we have. So this is our Lagrangian. If I convert it to this problem, okay, if I convert it to this problem, then we notice that this is our objective function. Then this is our inequality constraints. So if I try to plug this into our Lagrangian, now our Lagrangian will depend on, first is it will depend on the w. Second of all, since what we want to minimize here is we want to find what is the value of w and b that will minimize this whole thing, then this Lagrangian will also depend on the b value. Finally, it will also depend on your lambda. The question is, why doesn't it depend on nu? Solely because you don't have any equality constraints here. Okay, so you don't have equality constraints, you only have inequality. That's why we only depend on the lambda. This is defined as, this will be 1/2 magnitude of w squared. So this is just your objective function plus this will be the sum for all n from 1 to n, basically how many data points are there. We put, this is the Lagrange multiplier associated with that inequality constraint. Then we simply just plug in the inequality constraint, that is 1 minus Tn w dot xn plus b. Okay, so this is basically every inequality constraint that you have. Okay, so now we have already found out what is the Lagrangian. So this Lagrangian will depend on this w and b. Then we want to formulate the Lagrangian dual. So when we want to formulate this Lagrangian dual, notice that we want it to only depend on our dual variables. Here we only have one dual variable, that is your lambda, your Lagrange multipliers here. So then I will just formulate, this is our Lagrangian dual. Our Lagrangian dual now should only depend on lambda. That is, I will define this as script L lambda. This would be basically, we want to find what is the lower bound across every possible w and b that will find the lower bound of this Lagrangian function. Okay, so this is essentially the Lagrangian dual that we want to determine. If I want to expand this further, then I will find I want to minimize with respect to w and b the function 1/2 w squared plus sum over all n's of lambda n times 1 minus tn w dot xn plus b. Okay, so this is basically our goal. We want to find which values of w and b that will minimize this whole Lagrangian function. Okay, so now that we have this, we want to find the values of w and b that will minimize this whole thing. When we want to minimize, we always take the derivatives here. Okay, so we are going to solve this by taking derivatives. So this thing is minimized when you see that for every single possible w, we want to see whether I can find the value that will minimize the gradient across w. So that is, I want to determine the gradient factor of wb lambda, set this to be equal to 0. Essentially, if I differentiate this across every factor w, this should be equal to 0. And if I differentiate this with respect to b, this will be also be 0. Okay, so that is the condition where this is minimized. Okay, so I can also rewrite this whole Lagrangian if we assume that your x and b, your x and w will be a factor of dimension d. Then I can also rewrite the Lagrangian as a summation. So I can write this w, then wb and lambda. This will be equal to basically 1/2 sum of wi squared for I equals to 1 up to d plus the sum of, for every single possible n, we want to find lambda n multiplied by 1 minus tn, sum over every single, basically this is the dot product, so this is wi with the element I of data point xn plus b. Okay, so once I have this, then the next thing we want to do now is to just find the derivatives. So let's now find the first derivative, that is, we want to see whether I can differentiate this with respect to w. Okay, when you want to find the derivative with the gradient function, then it's easier to actually investigate how do you find the partial derivative of L with respect to every element wi. Okay, so this one actually can be easily done. We notice that this part is easily differentiated because now you only have one single wi that will be affected. So that's just simply, this will be wi, then this will be plus. If I expand this, then I will just need to differentiate this term. So this will be differentiate with respect to wi of sum over all n, lambda n, sum over all d, wi, lambda n tn, wi, x, and I. Okay, note that this will be negative because of the negative value here. Okay, so you can explore this further, but in the end you should get this value, which is just wi minus sum over all n equals to 1 up to n of lambda n, tn, x, and I. Okay, because now there is only one wi that will cause this to have a derivative that is non-zero. So this is now my partial derivative with respect to wi. Then I can now determine what is this gradient function. Okay, so if I do that, set this equal to 0, then this part is essentially just the factor w minus sum of, from n equals to 1 up to capital N, the Lagrange multiplier associated to that inequality, to that data point, tn, target of the data point, as well as that entire data point as a factor, should be equal to 0. When this happens, now you will realize that now you have a constraint, a new constraint that's introduced here, that is, when you optimize this, okay, when you find the infimum of this whole Lagrangian function, then it will only be a minimum when your weight factor is equal to the sum of lambda n, tn, xn. Okay, so that means that if I define a Lagrange multiplier here, then I'm going to take the weighted sum of every target multiplied by that data point. That is essentially our W. Okay, so I just need to train this lambda n. So this is our first constraint. The second constraint is obtained when we set the partial derivative of L against B. This should be equal to 0. Now notice that when we set this equal to 0, then there's only going to be one term that we will differentiate, that is the term with respect to this B. Okay, so if I write that down, then I will notice that this is just simply taking the partial derivative against B of this is negative sum over all n lambda n tn multiplied by B. Must be equal to 0. Okay, so when that happens, then you will notice I can just differentiate this directly. Yes, I can differentiate this directly. Then this will just be, I take the B outside, then now this will just be n equals to 1 up to n lambda n tn must be equal to 0. Okay, so now this will introduce me a new constraint. But notice that this constraint doesn't depend on the B. Okay, so once I have this, then I will just plug it back into our original Lagrangian dual. So this will be, we will put here, the Lagrangian dual that depends on just the lambdas will be infimum of W and B. I can put here basically our F0, which is 1/2 W squared minus this is the minus sum over all n lambda n multiplied by 1 minus tn W dot xn plus B. Here I can actually expand this further. Then I will notice that I will just find the infimum. It's not factor. Infimum of this will be 1/2 W squared minus, I will expand the bracket inside, so now this will just be lambda n. Now there's a plus here, so this will be plus a, oh sorry, this should be plus just now. Okay, so now this is just 1/2 plus this whole thing. So now this will be this is minus sum over all n of lambda n tn W dot xn. Then I will do another minus here, so minus sum over all n lambda n tn times B. So this is essentially after I expand all the entire brackets. So we have to notice something here. Note that when we want to minimize this whole thing against W and B, there exists this certain constant, okay, which is just lambda n tn and B. So if I want to minimize this whole thing, okay, if I want to minimize this whole thing, I can just set B to be a very high value. So if I set B to be approaching this approaching positive infinity, then I notice that this whole thing will actually overpower the original function. Okay, so to minimize this whole thing, I just need to bring B to a very high value such that now this will reach negative infinity. So we don't want that to happen. So I can say that when this has effect, okay, when this has effect, then this whole this whole Lagrangian dual will actually go to negative infinity. It will only happen when this whole thing is not equal to 0. But when this is equal to 0, as the constraint that is provided here, it might achieve a minimum value. Okay, so this whole thing I will just need to write down first. When this is not equal to 0, then Lagrangian dual will approach negative infinity. Okay, so this is just to note down. I will actually write this in a correct manner later on. So for this minimum value to exist, then this constraint must be satisfied. That is why this part would be actually equal to 0. Okay, so this constraint must be satisfied, thus this will be actually equal to 0. So I'll just plug in the values here. So I'll substitute this W with the value that we have seen just now. So note that this can be rewritten down as WTW, matrix multiplication of the dot product. Okay, so when this happens, then I can just rewrite this as I plug in the W here. So W is given by sum over all n, lambda n, tn, xn, transpose. Then I will multiply the same W here. So now this will be n equals to 1, lambda n, tn, xn. I will plus sum of all lambda n's. Then I will do another minus here. So minus sum of all n, lambda n, tn. Then this will be I will place here, this is the W, lambda n, tn, xn, transpose xn. Okay, so this transpose is solely because this is a dot product. So I can express this again and the matrix multiplication as this will be W transpose xn. Okay, so here notice that I will use a lot of n's. So to prevent that, to ensure that when I multiply lambda n to another lambda n, I want to make sure that these two things are different. So I will rewrite some items here. Instead of using n, I will be using m. Okay, this just to distinguish between one certain n from another n. Okay, this will be lambda m, tm, xm. Then this will be lambda m, tm, xm. Okay, so next thing to do is to just actually open this entire thing. So when you open this entire thing, you will notice that this part is now going to be a double summation. Sum from n equals to 1 to n, m equals to 1 up to n. I can just put this is lambda n, lambda m, tm, tn. So basically the constants are going to be out. But notice that this transpose will come first before you multiply to xm. So then I will place this in. Now this will be xn transpose xm. Okay. Then I will do a plus this thing. Oops. Lambda n minus this will be the sum over all n. Sum over all m again. So I'll just bring whatever constants outside of this summation inside the inner sum. Then this will be lambda n, lambda m, tn, tm. This will be xm transpose xn. Okay, one thing to notice is that since xn and xm are factors, then these are just the dot products. So the dot product is commutative. That means a dot b is the same thing as b dot a. So essentially these two things are similar. That's why I can just combine them into one single part. So this is half of this whole big ass summation minus this entire summation again. Then now this will just be negative half. So I'll just put the positive constant in front first. So this will be from all n, the sum of lambda n, minus 1/2 the sum of this whole thing. So this will be lambda n, lambda m, tn, tm. This is just the dot product. Okay, so now we already found out what is the Lagrangian dual. So in correct notation, I will define the Lagrangian dual as follows. So this Lagrangian dual will actually be a piecewise function that sets this will be equal to this whole thing that we have derived here. So this will only be present when there's a constraint that is satisfied. So the constraint is essentially the constraint that we eliminate the b term just now. This is satisfied if your sum of lambda n and tn is equal to 0. So this is the constraint that we have derived just now. This is your delta L, delta B must be equal to 0. Else, if this constraint is not satisfied, then this whole Lagrangian dual will actually just reach infinity. Okay, so this is our Lagrangian dual. Once we have derived the Lagrangian dual, then we are done with problem 2. Okay, so Why do we need the Lagrangian dual in the first place? Because we are going to convert the primal problem into what we call a dual problem. So what is a dual problem? Let me give a very quick detour here towards dual problems. If you are interested, please take these two math modules. Basically, there's an MA3252. This is on linear programming. Or if you also want, you can also take this MA3236, which is on nonlinear programming. Okay. So what is a dual problem? Sometimes you might have a primal problem that may be too hard to solve. Okay, so when your original problem is too hard to solve, we might want to investigate the dual problem to actually provide you a certain bounds of what the optimal solution could be. So let me give you a certain example here. Let's say you are an artist. You sell two types of artwork. One is a sketch, then another one is a drawing. So we assume that a sketch will take you about 2 hours, whereas we can use 5 pens, whereas a drawing will take you 5 hours and 10 pens. Okay, and then we also assume that each month you only have 80 hours to create artwork because you're a student. Then you also have enough money only to purchase 200 pens. Okay, so now if you sell each sketch at $10 and each drawing at 50, how many of each artwork type should you sell to maximize revenue at each month? So now let's try to come up with what would be the original problem. So the original problem is essentially we denote the math here, x1 to be the quantity of each sketch that you sell, whereas x2 is the quantity of each drawing that you sell. Let's define the objective function here. So we want to maximize the objective function, which is basically the price of each sketch. So this will be 10 multiplied by the quantity plus the price of each drawing multiplied by the quantity. We want to maximize this thing. This is your, for those who know economics, this is just your revenue, which now becomes our objective. But there are certain constraints that you have to adhere to. The first constraint is basically the number of hours that you have. Each sketch will cost you 2 hours, so this will be 2x1. Plus each drawing will take you 5 hours, so 5x2. This must not be greater than the number of hours you have each month. Okay, so this is the hours constraint. Second one is the number of pens. That is, each sketch will take you 5 pens. Each drawing will take you 10 pens. So this must not be greater than 200 pens in a month. So this is the number of pens you have. Finally, we also need to ensure that every single sketch sold must be non-negative. Every single drawing sold must be non-negative. Okay, so this is just to ensure that you will not sell like negative 500 paintings or something like that. Okay, so now this is basically our primal problem. Now we want to do the dual problem. Here is the thing. You want to maximize your revenue, but instead of maximizing your revenue, what if we try to minimize the cost? Initially, we only put basically the working hours here, right? And then also the number of pens. But instead of this, what if we try to do this? We try to set, because every single thing, like you heard the saying time is money, right? So everything has an associated cost. That is the economic problem. So we are going to set two new quantities here. Y1 is essentially what is the shadow price, or rather what is the price of your 1 hour working hour. Y2 is essentially what is the price of your 1 pen. Okay, we set this to be a certain price. What we want to do now is we will set this to be the price, then you want to purchase your resource. Each resource is essentially given this thing. You only have 80 hours to create artworks and also 200 pens. So that means the cost of you to fully achieve this is essentially 80 Y1 plus 200 Y2. This is essentially the cost of your operation, assuming that your working hour and your pen itself is priced at a certain point. So you want to minimize this thing. You want to minimize the entire cost. This is basically, for those who understand economics, this is your marginal cost. We want to minimize this subject to some certain constraints. Now the constraint is, instead of constraining it against the number of hours and the number of pens, this will be constrained against your prices. What I'm saying here is, remember that each sketch will take you 2 hours and 5 pens. That is, I want to set the cost of each hour, so this is the Y1, plus your 5 pen, this must be at least greater than equal to 10. So this is an important thing. Why must it be greater than equal to 10? If you want to imagine it in a certain way, this 10 is essentially the price that you put. Okay, this is the price that you actually assign. What we want to set here is, if I put this as less than equal to, then I can set this y to be very, very small towards negative infinity, then this whole objective is minimized. But you can imagine it this way. Instead of setting this to be less than equal to, you want to ensure that the market or the public or whoever the customers will value your hour and value your pen to be as high as possible. But in the end, this value must not exceed your 80 hours and 200. That's why we want to minimize the entire cost of working. Okay, so this is essentially saying the shadow price must be at least greater than equal to the price that you set. Okay, so whatever you set your actual value to be must be greater than equal to whatever the market is willing to pay you, which is your $10. Okay, then another one to set is basically for your artwork. Each artwork now will take 8 hours as well as 10 pence. So this must be greater than equal to 50. And finally, some other constraints that we set is that this must be greater than equal to 0, as well as your y2 must be greater than equal to 0. Okay, so these are the constraints. So notice this thing. Notice that just now we are constraining it against hours and pence. Instead of doing that as a constraint, we now constrain it against, this is your price of one single artwork, one single sketch, and this is the price of one single drawing. This is what we call the dual problem. Instead of maximizing the marginal revenue, we are going to minimize the marginal cost. And observe that actually your marginal cost at any point in time, this must be optimized such that it will never exceed the marginal revenue. Because now if you actually exceed the revenue, then something is wrong with your calculation, right? Because your cost should not exceed your revenue, else you just set everything wrongly. So this must be true at all times. It will be equal to the revenue, but at some point we want to ensure that our marginal cost must not exceed the marginal revenue. So in fact, you will see this inequality later on. So I'll just leave this whole thing here about the dual problem. One key takeaway of this is simply this dual problem can be used instead of optimizing the primal problem. You can convert it to a dual problem that may be easier to solve. Okay, that is essentially the whole thing. So this dual problem is essentially, after obtaining the Lagrangian dual, the Lagrangian dual will already eliminate any variables that is provided initially, right? Your W and your B is already gone, or your X is already gone. So by then, you will create another optimization problem. If the original problem is a minimization problem, then you just need to maximize the Lagrangian dual, subject to every single Lagrange multiplier associated to the inequality must be greater than equal to 0. Okay, so the reason of this constraint here is because we want to ensure that there is a certain property called the lower bound property. Okay, what is this lower bound property? Let's try to see here. This lower bound property is essentially we want to ensure, so this lower bound property is made such that we want to ensure that the Lagrangian dual, your lambda and the nu, at any point in time, this must be less than equal to the value of the original problem. Okay, so this is basically the lower bound property. The lower bound property is to ensure that this Lagrangian will be a lower bound for the optimal optimal value. So why is this so? I can actually prove it really quick here. So let's take the assumption that we given every single lambda I will be greater than equal to 0. Based on the constraint that we have, okay? So given this, then we also suppose that we have this x caret. This x caret itself is a valid solution. By saying that this is a valid solution, or for those who understand the math, this is what we call a feasible solution. So long story short, this is just basically an x that satisfies all constraints. Okay, so it satisfies both Fix must be less than equal to 0 as well as your Gix must be equal to 0. Okay, so given this thing, then I will derive two certain property here. That is, for any single inequality, this will be less than equal to 0, as well as for any single equality constraint, this will be equal to 0, because x itself is a valid solution. Now, given this whole thing, I can determine this thing. Note that in our Lagrangian function, your Lagrangian dual is essentially just finding the lower bound across all possible x of this f0x plus sum over all inequality constraints lambda and let me just put this as I. Lambda I Fix plus sum over all inequality constraints. So this will be I to P of nu I Gix. Okay, so this is our Lagrangian dual. Why is this helpful? Notice that the moment that this Gix is equal to 0, if x itself is a feasible solution, then I can say here, if x is a feasible solution, then Lagrangian of this with lambda and nu will be equal to f0x plus sum over I equals to 1 to m. This entire thing plus this entire thing as well. So this whole thing is essentially 0 because for any gi of x will be 0. Now the question is just this part. Is there any way that we can set this thing? We notice that fi of x bar, x caret, this is equal to 0. Thus, if we have any positive constraint, a positive constant lambda, any positive constant multiplied by any negative value, okay, this would be positive times negative will always be negative, right? Okay, so this will be less than equal to 0. This is a positive constant, this is a negative constant, a negative value. So then if you multiply a positive value to a negative value, this will also be less than equal to 0. Then I can have, this is just basically f0 of x plus sum over every single I to m of lambda I fi x, which is less than equal to f0 of x. Thus, for any feasible x, we always have that the Lagrangian function x lambda nu, this will always be less than equal to f0 of x. Okay, so this is basically the lower bound property. Now when this happens, then I will say that, notice that our Lagrangian dual will only depend on lambda and nu, which is equal to the lower bound of the Lagrangian function, which here is essentially, this will always be less than equal to any value of x lambda nu for any possible value. Okay, because this is basically the lower bound, right? Your Lagrangian dual is a lower bound of all possible Lagrangians given a certain lambda and nu. So that means that any possible value of x here would be greater than equal to the Lagrangian dual. That's what I'm saying here. Okay, so this will be greater than equal to the Lagrangian dual, which in return will be greater than equal to your x. Okay, for any value. So assuming that x star exists, okay, so assuming that we have an x star, this is an optimal point such that exists, such that if we have a primal optimal, p star exists, then I can have this Lagrangian dual would be less than equal to this x star, because note that x star is just any point x, right? Okay, so this is just any point x, which is less than equal to f0 x star, and this is just basically our p star. So this Lagrangian dual is always less than equal to p star. That is essentially what we mean by the lower bound property. For us to establish this lower bound property, we have to ensure that this lambda is greater than equal to 0, else we won't have this inequality. Okay, so that's just the key takeaway. Now with this lower bound property, we have certain important properties here. Oh, I will come down to that later. Okay, so we have certain important properties which we will show later. That is basically our weak duality as well as the strong duality, which is basically a tight lower bound. Okay, so now we want to convert the SVM problem into a dual problem. So if we want to write down the SVM dual problem, all we need to do is to just basically simply put in the template. That is, we want to maximize the Lagrangian dual with respect to any lambda and any nu of the Lagrangian dual. There's terrible handwriting. Subject to the constraint that any single inequality associated with a constraint must be greater than equal to 0. Okay, so this is basically the template that we have. All we need to do now is to just plug this inside. So our maximized value is we want to maximize the equation that we obtained just now, the Lagrangian dual, which we have just now. It was the basically for any lambda I minus the 1/2 sum over all n sum over all m of lambda n, lambda m, tn, tm, xn transpose xm. Okay, this is the function that we want to maximize subject to constraints. The first constraint is that we want to ensure this is greater than equal to 0 for all I from 1 to n. This is basically to satisfy the lower bound property. But there's another constraint that we have. The other constraint that we have here is essentially the, if you remember this is the lambda n tn. This must be equal to 0. Okay, so this must be equal to 0 because this is to satisfy your partial L over partial B is equal to 0. Okay, this is the constraint that popped up when we have our Lagrangian dual formulation, which is on this side. Okay, because of this, then we have to set this as a new constraint. So any important takeaway here is that any constraints that you set during the Lagrangian dual formulation must be included inside your dual problem also. Okay, so here I want you to actually pause a while and also observe. Note that now this only depends on your x dot x. Okay, so any data point x, take the dot product with any data point x again. So it's basically a pairwise dot product across every single possible x. Okay, so this will only depend on this xn xm, of course given a certain lambda. Okay, here notice that if you actually just take a step back and find out what is the decision boundary, your decision boundary now, initially we discussed that your decision boundary is essentially your this is your, if this w dot u plus b is greater than equal to 0, then it will be a positive. Or you also establish that it will be the, yeah, basically if w dot u plus b is greater than 0, then this will be a positive case. Now if I plug this w with the new optimized version that we found, this w is essentially just finding the Lagrange multiplier lambda n, tn, and xn. Then we are going to find the dot product of this with respect to u plus b is greater than or equal to 0. Okay? Or rather, I can also plug this into one single summation. Then this will be for all n, lambda n, dn, xn dot u plus b is greater than or equal to 0. Okay? So if I have any unknown x, if I want to find whether this is a positive case or a negative case, then I can just find the dot product of this new unseen case with every single seen cases. Then I multiply lambda n with Tn. Okay, then I sum them up. That is essentially the goal of this SVM. So this SVM essentially is whenever I see a new point that I haven't observed before, I take the dot product of this point across every single points that we have seen so far, see whether this is greater than or equal to 0. Okay. The reason we have this dot product is because now, the moment we found our dual problem formulation, which now depends on this Lagrange multiplier, what happens is we can actually determine this using this dot product can actually be applied with what we call the kernel trait. That is, instead of finding the dot product of this vector purely, what I can do is I can actually construct new set of features. So I can put this as a phi. I can instead pass xn to this feature first. Then I do the dot product of these two vectors. So essentially, any point, I take the position vector, or basically the vector itself, I'll pass it to this kernel function, then I will dot product this kernel function. So this is essentially, if you have heard the term before, this is also part of your feature engineering step. Because sometimes you want to also expand this further. Note that actually you don't even need to have both of these in vector form. You can actually just derive this together into one single value. That is, if I have this kernel function, kappa, I can just apply xn and u together. Okay. So the reasoning of this is because sometimes you can have an infinite dimension vector. So this kappa could, for example, be your radial basis function, where it will be an e of something. So that is where you can implement Gaussian features. Okay, so that is for us to actually increase the dimensions of our SVM. Okay, so now back to the problem here. We have already derived the dual problem. So we will also introduce another notation, which is regarding to the optimal value of the dual problem. So we denote D star. This will be the optimal value of dual problem. If you remember, P star is essentially the optimal value of your primal problem. So due to the lower bound property, since we have set the lambda I must be greater than or equal to 0, we know that this dual optimal must be less than or equal to your primal optimal. So this is what we call as weak duality. However, under certain nice condition, we can actually have your P star is equal to D star. This is what we call the strong duality. Okay, so in weak duality, your dual optimal will always serve as a lower bound of your primal optimal, but under certain conditions, you can have strong duality that will say that your dual optimal is actually equal to your primal optimal. So if my goal is just to optimize the function to get the value, then I can actually just solve the dual problem and I'm done. Okay, but normally, this dual problem is used to check whether it's feasible or not. For instance, you can have, say, if the primal problem is not solvable, then the dual problem will also not be solvable. And same goes the other way. If you can have a dual problem that is solvable, then the primal problem will definitely be solvable. So now we are going to go into another concept which we call the complementary slackness. So what does this complementary slackness tell us? Complementary slackness is when we implement this assumption that the strong duality holds. Okay, I repeat, complementary slackness is when we have this assumption that strong duality holds. That is, there is a P star that is equal to your D star. When this happens, then we also have an optimal point X as well as the optimal points lambda and nu for the dual problem. So we set X star to be the optimal solution for your primal problem, lambda and nu star to be the optimal solution for the dual problem. Then, since we have assumed that the strong duality holds, then I can say P star will be equal to D star. What is P star? P star is essentially, if you have your X star, I'm going to pass this to my objective function. This is your P star. Okay? Whereas for your D star, this is just, I find the Lagrangian dual, I pass down the optimal values of my lambda and the optimal values of, start this up, say, optimal values of the lambda and optimal values of the nu. Okay, so this is essentially the values here. Note that I can expand this Lagrangian dual further to say that this will be the lower bound across every possible x of f0x plus sum of every single possible lambdas with fi. So this is the inequality constraint plus for every single equality constraints. So this is star, star. Okay, so this lambda and nu is the star ones. Then I will set this to be from 1 to m. This will be from 1 to p, number of equality constraints. Okay, so notice that this will be the lower bound. Okay, Lagrangian dual is a lower bound for any possible value of x. Thus, since we have one x star, this x star is considered a value of x also, right? This lower bound would be less than equal to our f0, if I just put in x star here, plus, I will just skip the summation process. This is the lambda I fi x star, plus this is the sum of every single possible nu I star gi x star. Okay, so this thing. Now, we also noticed that previously, we have defined that there's a weak duality condition. Weak duality will tell you that, let me just write here. Weak duality tells us, sorry, not the weak duality, but the lower bound property will tell us lower bound property will tell us that if my lambda is greater than or equal to 0, then I will have this property which tells us that any value of x, if I pass it to the Lagrangian function, this will be less than or equal to f0 of x. Okay, so this is the lower bound property, assuming that x itself is visible. Thus, I will say that this is our Lagrangian function. This part is essentially our Lagrangian function, taking x star, then putting it with the lambda star and the nu star. Okay, so I know that by the lower bound property, I will have that this must be less than or equal to f0 x star. Okay, so this is where the lower bound property comes in. So when we have this thing, we notice that this Lagrangian is sandwiched between f0 x star, so this Lagrangian is greater than or equal to the f0 x star, and this is also less than or equal to f0 x star. What this is telling us is that L x star, lambda star, and nu star, this must be equal to f0 x star. Okay, so I'll just reiterate. By this property, we have seen that this Lagrangian value must be equal to f0 x star. Okay, one important thing to note here is by setting this definition, note that at this point, whatever x that minimizes this Lagrangian, there can be multiple x. What we are saying here is that x star must be minimizing this Lagrangian function. Okay, so this must be one of the minimizers. Okay, it can be possible that there might be many values of x that will minimize the Lagrangian function, but what we are saying is that x star must be one of the values of x that will minimize them. Okay, so given this, the next thing to do is to just expand this further. So I will have this is my f0 x star plus the sum for all lambdas fi x star. So this is the inequality constraints plus the sum over all equality constraints. This must be equal to f0x. So here, I can subtract f0x from both sides. Then I will notice that this will just say, for every single lambda I fi plus for every single nu I gi, this must be equal to 0. Another thing to note that since x star is a solution, right, which is also a valid solution, we know that gi x star, this must also be equal to 0. So essentially, if you multiply nu I with any gi x star, since x star is a feasible solution, then this will also be 0. Thus, if I bring this further down, then I will notice this is just simply saying that every single lambda star fi x star, this must be exactly equal to 0. Okay, so because this whole sum, this whole term is essentially equal to 0, that's why I can bring this down, then this will just be equal to 0. Okay, so at this point, one other thing that we have to notice is that, again, since x star is also a feasible solution, then I will notice that this fi x star would be less than equal to 0, following the inequality constraint. Okay, but we also notice that this lambda has been set to be greater than equal to 0. Okay, so let me just write this maybe for you to be able to understand. This is basically the dual problem constraints. Because we note that lambda star is a solution to the dual problem. This is our primal problem constraints, inequality constraints. Since x star itself is a valid constraint, then this is just your primal equalities. Okay, so because of this dual problem constraint and the primal inequality constraint, what we have now is if I multiply them, then you will notice that just now we have discussed lambda I star multiplied by fi x star. This will always be less than equal to 0 because you are multiplying a positive value to a negative value. Then this will be less than equal to 0. So for me to say that if the sum across every single lambda times fi is equal to 0, noting that every single item here is less than equal to 0, then this cannot be a negative value. Because for it to be equal to 0, any negative value must be offset by any positive value, right? So this will cancel out each other. But if everything here must be a negative value, okay, must be a less than equal to 0, then there's no way that there should be a negative value that's not 0 here. Then that is telling me that, therefore, lambda I star fi x star, this must be equal to 0. Okay, maybe I just put another color here. So what I'm saying here is basically, because this summation must be equal to 0 and each item here must be non-positive, therefore lambda I star fi x star must be equal to 0, assuming that the dual problem and the primal problem has an optimal solution. This exact condition is what we call the complementary slackness. So what is a complementary slackness? We have to first investigate what is the definition of a slack. Slack is essentially telling you that, for example, when you say you're doing your work, then you are slacking at your work. That means you are not really fully concentrated, fully focused, fully optimized, right? Okay, so this slack is actually referring to the inequality constraint. Okay, when we say an inequality constraint is being slacked, that means this is basically not active. Okay, same goes with like a person or your co-worker. If your co-worker is slacking, then your co-worker is not actively doing things. Okay, in terms of saying an inequality, say for example this is our inequality, then the region is here. Okay, when we say that a solution will cause this inequality to be slacked, that means the solution is somewhere here in the region. The moment that it is active is when it hits the exact solution. Or rather we say, if I have, if x causes fix to be active, then you will have this Fix must be equal to 0. Okay, so the moment that this inequality is active is when the equality is satisfied. That is when we call it active. Okay, so when we say complementary slackness, this means that lambda I star times Fix star, this must be equal to 0. So it can only mean two things. Either the Lagrange multiplier, the optimal Lagrange multiplier associated to this constraint is equal to 0, or you can have this condition also, this Fix star is equal to 0. This Fix star equals to 0 is when it is an active constraint, or it just doesn't have any Lagrange multiplier. Okay, so it either is an active constraint or it doesn't have a Lagrange multiplier. So say for example, if I have this is our inequality constraint, is the similar graph that the prof draws. Okay, so this is our inequality constraint, then it's basically the region inside here. Let's take 3 points. Say for example, this is the first point, this is the second point, this is the third point. At this point, I know that the constraint is active because it is exactly at the bound. So Fix star, this will be 0. That means we can have lambda I x star, lambda I, this can be a non-zero value. The moment that this happens, okay, any value here is when the constraint is not active. If the constraint is not active, then that means that there won't be a Lagrange multiplier. So this Lagrange multiplier lambda I star must be equal to 0. Okay, for that constraint. Any questions? It's not a tutorial, sorry. Okay, yeah, so basically that's just to sink in. It's either the constraint is active, then you have a non-zero Lagrange multiplier, or the constraint is not active, then for that point you will have a 0 Lagrange multiplier. Okay? Yeah, I hope this will be quite clear for you. So, we want to see how do we interpret complementary slackness in terms of SVM. Let me just draw the similar setup just now, the Holy Grail setup. This is our decision boundary. Then we have the, basically this is the bounds. Then this is a positive sample cases. Then this will be the negative, but this is our positive cases. Then this will be the negative cases. Okay, so this is essentially the bound. Our constraint just now in our primal problem, the constraint is that basically our Fi's, this is saying that 1 minus Tn of W dot Xn plus B must be less than equal to 0. Okay, this is the constraint that we have. What this is saying is that either your X must fall in, let me use another color. So either your X must fall in this region, or your X must fall in this region. It should not fall within the region that is sandwiched within the bounds. Okay, so either your X must fall within the region below the bound or above the bound. It cannot fall in this region. So with this constraint in mind, then here's the thing. My question now is, which values of these samples will give you an active constraint and a non-active constraint? Okay, see here, this is not within the bound, so this will be an inactive. This will give you an inactive constraint. Whereas for here, this will be located at the bound, so this will be an active constraint. Okay, that's it. So this will be an inactive constraint, this will be an active constraint. Thus, it will tell you that basically for all data points xn, if this xn is exactly at the bound of the SVM, then it can have it may have a non-zero Lagrange multiplier. But if xn is not at the bound, then you know that your lambda n will be equal to 0. Okay? Which here this only works assuming that strong duality holds. Okay, so assuming that your strong duality holds, it's either two things. Either your data point is exactly at the bound of the SVM, then you have a non-zero Lagrange multiplier, or if the data point is not within the bound, so if it's at one of the regions, then you have a 0 Lagrange multiplier. Okay, so let that sink in. That means if I want to train this model, I only need to find what is the Lagrange multiplier associated to the points that are within the bound. Because the rest I know this will be 0. So if I have, say for example, a lot of data points, call it this way. So if I have a lot of data points, let's say this will be the negative cases, then some positive cases will look like this. Let me just do it like this. Okay, so that means if I draw the SVM for here, if my SVM would look something like this, then all I need to keep track of is essentially what is the Lagrange multiplier associated to this point and this point. Because I know for every single part here, for any other part, this will be 0. For any part here, this will also be 0. Okay, remember that our model, our decision boundary here is just basically your W dot any data point you see plus B must be greater than or equal to 0, something like this. Okay, or maybe minus 1 equal to 0, greater than or equal to 0. Then if you put the W inside, then this will be your, just now we have seen, for any single for any single sample in the data set that you have trained on, lambda n, Tn, xn dot u plus b minus 1 greater than or equal to 0, something like this. Okay, maybe we remove the minus 1 for now. Notice that for any part, for any data point that is not within the bound, this lambda n is equal to 0. Then your calculation will actually be very, very fast, because all you need to do is just count the dot product of the factors that are within the boundary. Okay, I repeat, all you need to do is to find the dot product of the factors that are exactly at the boundary. What factor do we call this? For any xn that will have a non-zero lambda n, we call this as the support factor. Hence, we have the term support factor machine, because only these factors are actually matter inside your calculation for the decision boundary. All the others, they will not give any contribution because their lambda is equal to 0. But only these factors, the one that establishes the bound, is where they will have the non-zero lambda n. These are what we call the support factors. Okay, so this will give you two properties. First of all, is only the support factor matters. Second of all, another thing to note is that a lot of your data points will have lambda equals to 0. That's why if you model every part of the Lagrange multiplier from lambda 1 all the way to lambda n, most of them will be 0. Only certain parts, only these will have a non-zero lambda. That's why our model itself stores the lambdas, right? So our model will store the lambdas, and then most of them will be 0. So this will be a sparse matrix, because a lot of them are 0 except the support factors. Okay, so I hope that clarifies on why SVM is called a support factor machine, as well as why it is a sparse model. So finally, let's discuss about the KKT conditions, which we call the Karush-Kuhn-Tucker conditions. So the KKT conditions is what we basically a set of conditions that will also hold when, I have to write this down again, when we assume that strong duality holds. Okay, so when we assume that strong duality holds, we mean that x star is a primal optimal value. Sorry, x star is a primal optimal solution. Then we have your lambda star and your nu star. This will also be a dual optimal. Then you will have your P star is equal to D star. Okay, so these are the three conditions here. When we say strong duality holds, it means that the optimal solutions for the primal and the dual problem must exist, and we have the optimal values are similar, are equal. Okay, so that's our assumption here. Now we note down that the moment that this assumption is true, okay, the moment that this assumption is true, just now we have seen when we did the complementary slackness calculation, we note down that there would be this P star is equal to D star, which at the middle step, you will notice that this infimum XD of your Lagrangian must be less than equal to, this part must be less than equal to the optimal x star, which in the end this is equal to your f x star. Okay, so this was what we have shown just now. Just now this is basically your f0 x star. Yeah. If you're interested, you can see back again the complementary slackness part. So basically this thing we have shown earlier. So here, because of this thing, since this f0 x star and this is also sandwiched by f0 x star, then it can only tell us one thing. It's basically saying that this Lagrangian dual, okay, this Lagrangian dual, your lambda star, or maybe I'll just put the infimum directly. So the infimum of any xd, lx star, lx, then lambda star, and your nu star. Basically for any x, if I find the minimum value, this must be equal to the Lagrangian if I apply this with the optimal primal solution. Okay, so essentially, this x star must minimize L. Okay, since this is equal to your P star, since this is your D star, which in the end is equal to your P star, right? Then I must have, if I apply the x star to my Lagrangian function, whatever value I obtain must be equal to the infimum of L, x, lambda star, and nu star. Okay, so this must be equal to the lower bound that we found. Okay, just let that sink in. Basically, it must be equal to the lower bound. So x star must minimize L. When this happens, then we know that if it minimizes L, just now we have seen that when we want to minimize things, we are going to use the first derivative. So if it minimizes L, then I must say that I can take the derivative of L with respect to lambdas, with respect to your x. Okay, so this is basically the derivative of L with respect to x. This must be 0 at the point of x equals to x star. Okay, I repeat, because this x star must minimize the Lagrangian L at the point x equals to x star, this derivative must be equal to 0. Okay, yeah. So when this happens, then I can find the derivative, which is saying that this will be my x star x, the derivative of f0 with respect to x. So if I plug this x star inside, plus basically the sum of all the Lagrange multipliers from I equals to 1 up to m, if I multiply, if I find the derivative of fi, then I put in x star, plus this is basically my I equals to 1 up to p, I put in the nu I star, this must be equal to 0. Okay, so this is just the additional condition that we have. It's essentially saying that the moment this holds, then x star must minimize L. That's why the gradient must be 0 at the point x equals to x star. So this is what we call the vanishing gradient property. Okay, so now let me just recap a bit on what are the KKT conditions. What is the Karush-Kuhn-Tucker conditions? So the first condition for this Karush-Kuhn-Tucker is that there must exist an optimal solution x star. Okay, so basically there must exist an optimal solution for your primal problem. Thus, this means that your x star must be feasible. This is what we call the primal feasibility. Okay, that means that for this solution to exist, one preliminary condition is that your x must be a feasible or a valid solution. Okay, this will give rise to two additional constraints here. One is your x star must satisfy all the inequality constraints. Okay, it must satisfy all the inequality constraints. That means for every single I in your inequality constraints, this must be satisfied. Okay, so that's the first condition. The second condition is that your x must satisfy all your equality constraints. Okay, so for any equality constraints, your optimal solution must give gi equals to 0. Okay, so this is basically your primal feasibility. The second condition now is about your dual optimal. So we are saying that when d star exists, we must have that lambda star as well as your nu star. This must also exist. And for it to exist, it must satisfy your dual problems constraints. Okay, so for the dual optimal solution to exist, it must satisfy the dual problem constraints. This is basically what we call dual feasibility, as in the solution must be a feasible solution to your dual problem. Okay, so the only constraint that we have for our dual problem is simply your lambda I star must be greater than or equal to 0 for any inequality I. Okay, so this is basically the dual feasibility. So the first one is to say that your x must be a feasible solution. The second one is saying that the lambda and nu star must be a feasible solution to the dual problem as well. Third one is when this p star is equal to d star. So when your strong duality holds, complementary slackness must also hold. Okay, so this one we have shown just now. So complementary slackness must also hold. That is saying either your data point itself is located on the boundary, so it's an active constraint, or you will have your Lagrange multiplier is equal to 0. Okay, so complementary slackness must hold. That's saying either the Lagrange multiplier must be equal to 0, or this inequality constraint must be active at the optimal solution. Okay, so this must be equal to 0 for all inequalities. And finally, we have shown earlier also that when this p star is equal to d star, your x star must minimize L. Okay, so this is saying that x star must minimize L. Thus, this will tell you that it must be a vanishing gradient. So the gradient must be equal to 0 at the point of x equals to x star. Okay, so this is just saying that if I set the gradient here, then this will be taking the gradient of f0 x star plus the sum of the lambda i's star gradient of fi passing x star plus sum of all nu i's passing the pass in the x star to the gi. This must be equal to 0. Oh, this is the gradient of gi. Okay, so another important thing to note here is that this vanishing gradient assumes that your functions itself must be differentiable. Okay, because you have to differentiate this. That's why your f and g must be ensured to be differentiable. Okay, so what we are saying is that if strong duality holds and we have the optimal solution to exist, then all these four conditions must be satisfied. This is essentially what we call the KKT conditions. Okay, so just to reiterate, your KKT conditions is saying that it must be a feasible solution to the primal problem. So x star must be valid to the primal problem. Your lambda and the nu must be valid to the dual problem. Then complementary slackness must hold when strong duality holds, as well as the gradient must be 0 at the optimal solution. That is your KKT conditions. Now, it is an important concept here that says that the converse of this isn't true. That is, if strong duality holds, then these four conditions must be true. But if these four conditions are satisfied, it might not say that the strong duality holds. Okay, so it's just basically if strong duality, then it implies KKT must hold, but not the other way around. Okay, so the relationship between optimality is basically when you have a strong duality. Okay, so when the strong duality holds and we have an optimal solution, then the KKT conditions must hold. But for you to converse, if the converse isn't true, but rather it will be true if your f specifically is a convex function and your g is a affine function. Okay, just to maybe show a brief idea on what a convex function is. Suppose that this is your f. Okay, this is your f. Say I take two values of x, x1 and x2 within, or maybe xi and xj within the set that satisfies your f. So xi and xj that satisfies f. I'm saying that if I take wherever within this xi and xj, okay, if I take any point within this line segment, or I can denote this by saying I can put a parameter here, parameter xi plus 1 minus lambda, 1 minus theta xj, this must also satisfy f. Okay, so this is basically what I'm saying. Any point along this line segment must satisfy f, then this will be a convex function. You can think of it like this. If I have, say for example, this is a jelly bean look alike. Okay, so if I take 2 points, say for example this and this, but then if I take any point along this line segment, there might be a point where it doesn't actually satisfy my f, because now this is already outside of the boundary, so this is not convex. It will only be convex if any point within that line segment will be inside my boundary. So this one, the important thing to note is that your theta must be within 0 and 1. What do we mean by affine? It will be an affine function if, for example, this will be say a line. Then if I take any 2 points along the line, say this is xi and xj, which satisfies g, then if I take theta of xi plus 1 minus theta of xj, this must also satisfy g. Okay, this must also satisfy g, then this will be an affine function. But the condition is that this theta now can be basically any real number. So note that for convex, your theta is between 0 and 1. Here, your affine function is, it will be any real number. In terms of linear algebra wise, you will notice that this is basically a linear combination of any single point. Okay, linear combination of every single pair of points inside the G. Then this will be affine. So it's also important to note here that your convex function is essentially a subset of your affine function. If it is convex, then it will be if it's convex, then it will be affine. But the converse might not be true. Okay, so under the condition that your f is convex for all i's, so for your objective function and the inequality must be convex, and the g is actually affine. If KKT conditions hold, then it will be optimal with strong duality. But I think the second part you don't have to focus much. The only thing is that when strong duality holds, then the KKT must hold. Okay, so if you are curious, you also note that the SVM problem, okay, the SVM problem initially, your F itself for the, let me show, okay, it's a quite long tutorial. So for the original SVM problem that we came up with, notice that this is just the square. So by default, this is a convex function. Then here, this is just a line. So this will also be a convex function. That is why for the SVM problem, actually your strong duality will hold. Okay, so that's just something to note here. Okay, that was a long, almost 2 hours tutorial video. So I will just need to put a quick summary here. Essentially, what you need to know about the duality and KKT conditions is that, first of all, for an optimization problem to be combined together so that we don't have to bother much about the constraints, we can actually put them into a weighted sum, which we call the Lagrangian function. Then we can eliminate the variables itself, the original variables. We can actually eliminate them to just consist of the dual variables, which are basically our Lagrange multipliers. So the dual problem is essentially to find what are the optimal Lagrange multipliers to optimize the Lagrangian dual. Okay, so the Lagrangian dual is formulated when the optimization problem is in standard form. We can find this dual function essentially by minimizing the Lagrangian function with respect to any single x. So now the dual variables are just our Lagrange multipliers. We want to maximize the Lagrangian function with respect to the Lagrange multipliers, subject to every single lambda must be greater than equal to 0. This is to ensure, sorry, it's not the weak duality. This is to ensure that the lower bound property is satisfied. Okay. This lambda I greater than equal to 0 is to ensure that the lower bound property is satisfied. Then we also introduce two notions of duality conditions. One is the weak duality, which is achieved when your lambda is greater than equal to 0. But we also have another condition which we call the strong duality. That is when your primal optimal is equal to your dual optimal. So when we assume that the strong duality holds, then your KKT conditions must hold, which tells you that x star must satisfy the original primal constraints, lambda star must satisfy your dual constraints, then complementary slackness will hold, that is either this is active or your multiplier is equal to 0, and finally the gradient at x equals to x star, the gradient of the Lagrangian must be equal to 0. Okay, we also finally shown that the relationship of KKT with optimality is that when your strong duality holds and it's an optimal solution, then KKT must be satisfied. Okay, so that's it for this video. Thank you for watching and I hope you understand. Bye bye.